Hi, my name is Chad, and this is your Zero to Hero Kubernetes Fundamentals course. Now, as your instructor, you should know I am CKA and CKAD certified. I've also been an education specialist for 20 years, which means that I have spent the majority of that time in actual classrooms with actual students, not just from talking behind a camera. Which means the content of this video has been tested, bloodied, and proven to work for many folks that are looking to get started in Kubernetes. So the plan in this video is that we are going to be going through all of the fundamentals of Kubernetes, everything that you need as a foundation to pass your CCAD or your CKA exam, or if you're just looking to get proficient with Kubernetes in general. Now batter up, because here's the pitch. This video is a great starting point, but if you are looking for hands-on labs, AI support, human support from folks like me, then get yourself over to Alta 3 Academy, where we offer full courses which will cover everything you need to know about Kubernetes, including mock exams and everything that's needed for the CKA and the CKAD exams. That link is inside of the description, and I would love to see you there. Here is a list of all the content that we're going to be talking about inside of this video. If you're already somewhat proficient with Kubernetes, use the timestamps in the description to be able to hop to whatever it is that you need to learn. However, if you are new to Kubernetes, I strongly suggest that you just go through the content in the order that it is presented. You ready to rock? Let's get started. To begin, before we start getting into the what is Kubernetes and the how do I use Kubernetes, let's talk about the why even use Kubernetes. Kubernetes is all about enabling a certain sort of lifestyle in application deployment. Consider this, that ultimately it comes down to we've got some code along with dependencies that are needed in order for that code and its application to run. In a style of application deployment known as microservices, that typically means, hey, let's put all of that code and its dependencies inside of an isolated environment called a container. Now, that comes with a whole bunch of advantages. It's really easy to spin up containers, and if you have any experience with Docker, that's great. If you don't, that's not a problem at all. It's really easy to replace containers, which means that if you need to update or make changes to these applications, that can be done in a snap. And then there's the whole joke, oh, it worked on my computer, then we'll ship your computer. That whole joke is pretty accurate into what containers do. That if you create it so it works inside of one container, then it should work when you deploy it elsewhere. And a big part about what's cool about containers is that they are scalable. You can create as many different copies of them as you want. Thing about containers is they are not meant to hang around forever. Whether they die because you tear them down or because something happens to them, I mean, that's sort of an inevitability. And while there certainly are manual ways to deal with things like that, here's where we start getting into some more problems when it comes to container management in the traditional sense without Kubernetes. So a container, in order for it to work, has to run on top of an existing environment. So let's say a virtual machine. And you can create as many containers inside of this virtual machine as you want, so long as resources permit. But eventually you're going to get to the point where, oh, I don't have any more room for containers. Your virtual machine is tapped, but you need more. You still need to scale out. Well, let's talk about how that could lead to a couple of different disaster scenarios. Scenario number one, your host machine runs out of resources. You don't have any more room for containers. And as a result, containers may not be able to expand. Issue number two, containers die and they get ignored. There are ways for you to work around this, but you have to work fairly hard. And spoiler alert, this is something that Kubernetes can handle for us. And the third scenario is that all these containers are running on the same virtual machine, right? So if your virtual machine dies, no! All those containers just went down with it, and there's nothing that's set up in order to bring those back. Fortunately, Kubernetes has an answer. Here's where we might be taking your prior knowledge about Docker and applying it to how it works inside of Kubernetes. Containers in Kubernetes work exactly the same way they always did, whether they're being created by Docker or something else. But Kubernetes containers are placed inside of Kubernetes objects called pods. Pods are really just wrappers that are being placed around containers. Kubernetes manages pods, not containers. So by putting them together as one unit, it makes it easier to control. So that package deal, that pod and container, still needs to live on top of some environment. The container needs to draw its resources like we saw before. Traditionally, that can be on a virtual machine. In a Kubernetes environment, when you add virtual machines to it, those are called nodes. And you can add multiple nodes to the same environment. When you do that, you wind up literally exponentially increasing the total amount of resources that might be used for lots of pods. And when you combine all of those nodes together, you get what are called a cluster. Now, there are two flavors of nodes. The ones in green on my screen right here, these would be our worker nodes. And this is where you would expect to see the vast majority of pods, which remember are wrappers around containers, to be created. And as you can see, there can be more than one pod on like a given node. There can be a disproportionate number of pods on these different nodes. Some of these nodes may be in different sizes, like the one on the right is smaller, therefore maybe it can only fit one pod, whereas the one on the left is bigger and that one can hold 3. A cluster is just an aggregate of resources. Now, the other type of node, which is again also a virtual machine, is known as the controller. The controller does exactly what it sounds like. It is the hub of all of the tools that are required in order to keep your cluster running, and we're going to talk more about those later. As a general rule, you don't want to be just willy-nilly putting pods on top of the controller node. Why? Well, because the controller node's busy. It needs its resources to, manage the cluster, which is pretty important. Now, before we get to the fun stuff and before we actually start building pods and things like that, it is important to have an understanding of what is going on under the hood, what's ticking and running inside of these nodes, and what tools are we using in order to access and interface with our Kubernetes cluster. The first tool that we need to learn, and one of the many things that starts with the word kube, because Kubernetes just loves putting kube in front of everything, is kube control. And kube control is the CLI tool that is going to be installed inside of your personal workstation, your laptop, wherever it is that you're working from. That is where kube control is installed. And what that enables you to do is that from your machine, you are able to access the cluster. Note that we're doing so by connecting to the controller node that we spoke of earlier, and that all kube control requests are going to be received by the API server. So all communication inside of Kubernetes is done through an API, which if you know about APIs and HTTP and all that stuff, great. If not, it's not a deal breaker, but we'll talk about why that's going to be relevant later. Now, in order for kube control to talk to a given cluster, after all, what's stopping somebody from installing kube control and talking to any cluster in the world, is that it must be configured to do so. So if we take a look, what you see here in miniature is a kube config file. This is a document that should be on the same machine where kube control is installed. And it includes such things as like the location of the cluster, but also includes where is the certificate and key file, again, located on your personal environment, that will allow you to authenticate who you are and talk to that cluster. Without that setup, kube control is never going to work. But moving on through the anatomy here, talking a little bit more about the API server. Like I said, all communication, like all action that occurs inside of a cluster is done through an API, which means that a request is sent to the API server. It decides whether or not that request is valid, and then as a response will take certain action or return certain information depending on what it is that you're trying to do. So the API server is what will be returning information to you here at KubeControl. It is what also reaches out and communicates to every single node that are part of our cluster. Remember, you can have multiple nodes, multiple virtual machines, all part of the same cluster. The API server is also the only thing that talks to etcd, which is what we'll talk about next. All right, we're here on the official etcd website, which means that this is definitely third party and it's not just something that got invented by Kubernetes. etcd was around long before Kubernetes was. And what is etcd? It is a strongly consistent distributed key value store that provides a reliable way to store data that needs accessed by a distributed system or a cluster of machines. Well, you just described the cluster there, right? Distributed system of cluster of machines. So etcd stores state. It's all about storing data. So specifically when it comes to Kubernetes, where is it being written? How many nodes are attached to a cluster? Where is it written how many pods are running? And are they actually running? Or are they erroring out? Like, where is it written that whether or not pods are able to talk to each other and things like that? Just etcd. And as a result, etcd is something that as either an administrator or as a developer when it comes to Kubernetes, you should be very respectful of it. Because losing etcd is like lobotomizing your cluster. You are going to lose all track of all things that are running inside of it. Another component that is part of the controller is the scheduler. And what this is doing is that it's put this pod up on this node right here. No, okay, like Tetris theme. What happens to pods is that they get put on nodes, right? Well, what makes that decision? Sure, we can make that decision ourselves, but as a result, we want Kubernetes to decide that. So the scheduler is what's going to try to make sure that you've got like an equal distribution across your nodes for the most part, plus obeying any sort of rules that get put in place either by you or by the system itself, just to make sure that everything is following the rules. Speaking of following the rules, there is the controller manager. You might picture the controller manager as like the sheriff. I'm here to make sure all you pods stay in line. I'm here to kick butt and chew bubblegum, and I'm all out of bubblegum. The controller manager actually manages a lot of different daemons that control a lot of the behaviors of how your cluster runs. Now, if you're brand new to Kubernetes, these may not mean a whole lot to you right now, but for instance, objects in Kubernetes are tracked via namespaces, that they can be controlled through role-based access control, which are connected to service accounts, that you'll be creating copies of pods called replicas. That's something that needs to be tracked as well. And the controller manager is what's in charge of all of that. Now, kubelet. Kubelet is present on every single node inside of your cluster. And regardless of what this diagram might be showing you, kubelet is also present on top of the controller nodes as well. But kubelet is kind of like the eyes and the ears of every node inside of your cluster. It's responsible for all sorts of things, making sure that the containers are started, stopped, or restarted appropriately on each node in your cluster. Any instruction that comes from the controller node is going to be received by kubelet. So suffice it to say, if kubelet encounters problems on one of your nodes, well, then your node is now in trouble because that is your sole connection to the rest of the cluster. And now what about Docker? A lot of people say, well, should I be using Docker or should I be using Kubernetes? And if not Docker, some other container runtime engine. Here's the thing. It's not either or. If you're using Kubernetes, you are using Docker or Containerd or whatever. Because here's what's happening. All those pods that are being created on all those nodes inside of your cluster, remember, inside of those pods are containers, just exactly as we've always understood them. What's building those containers? Is it Kubernetes? No, absolutely not. because installed on every single node inside of your cluster is going to be some container runtime engine, whether it's Docker or something else. Which means if you've ever used Docker and you've used such commands as docker run or podman, like podman run, which creates containers, guess what? Those commands are still running in Kubernetes. But who's writing them? Not you. Kubelet. So Kubelet, our boy that we were talking about earlier, is what is responsible for all of these Docker or whatever commands that start, stop, restart, gather information about, but they are still using that container runtime engine. And what that means is that the life cycle of containers as we understand them still absolutely apply inside of Kubernetes. You still need a image, which is to say like a picture, a template for how a container should be built and the application inside of it should be set up. And images still need to come from somewhere, from some place of storage. Those are called registries, and that, of course, can be configured to all sorts of different places. Now, let's put all of those moving parts together, and let's see how does it wind up that if we say make a pod, that those... Now let's bring all that together, and let's see what would happen when we actually use kube control to make a pod inside of our cluster. Step number 1, and of course we'll be doing this ourselves like real soon. We use kube control commands to create a pod. We'll talk later about how you're going to write a document called a manifest, and that'll include all of these instructions on what Kubernetes is supposed to do and how it's supposed to build it. So that information is taken to the controller in this east-west diagram. You can see that right here, which of course is received by the API server. You can see just how much traffic goes to this API server. It's quite popular. The API server will then turn to etcd, and assuming it doesn't just reject your pod plan outright because there might be typos or you might not have authorization, yada yada, if it passes all that, then it will tell etcd, hey, here's the pod we're going to make. Etcd sends back a response. 200 in HTTP speak means thumbs up. Sounds good. API server then sends a response back to you at your command line saying, yeah, looks good, boss. We're going to go ahead and make that pod. But is the pod made yet? No, not by a long shot. What happens next is that our API server needs to know where is this pod going to go. So it goes to the scheduler. And assuming that our manifest did not say explicitly where we wanted the pod to go, the scheduler is what is going to make that decision. Let's go ahead and put that on top of worker node number 2. So just remember, worker node 2 is the decision that got made. That's sent back to the API server. API server says, okay, sounds good. I'm going to let etcd know that we're going to put that pod on node 2. etcd says, sounds good, boss. And then API server says to the scheduler, hey, good pick. We're going to wind up going with node 2. So it's a lot of back and forth, all right, as we are ascertaining where resources are going to be located physically inside of our cluster. From there, our API server, which again is inside of our controller node, is going to reach out to the worker node where we decided we wanted to make the pod in the first place. Remember how we said that that might have been worker node number 2. So the API server sends that to Kubelet, specifically Kubelet on worker node number 2. Kubelet says, got it, boss, and then turns around and runs all of the necessary commands like docker run or container dstart, like whatever the command is. It's Kubelet that's handling that for us. And as a result, it is only at that moment that a container is actually built. And it's also Kubelet that's responsible for making the pod that the container was put in. So it's not a question of which came first, chicken or the egg. It's definitely clear. Pod is made first, container is made inside of it second. And what Kubelet will constantly do is that it will be feeding status updates as the container is being built, as the container is finished, as the container enters an error or stop state. Kubelet is perpetually providing that information back to the API server, which then will in turn make sure that that information is being recorded to etcd. So it's a really nifty little ecosystem of what's happening here. And having an understanding of what these components are and how they work together can really help you troubleshoot and better understand how to make the resources and make sure that they are working and healthy inside of your cluster.